Okay, guys, in this video, we are going to learn how to draw the derivative vector, so the position vector and the derivative vector, and also how to find the unit tangent vector, which is not that difficult. Okay, first thing we're going to do is find the derivative vector. So as I was explaining to you, derivative of a vector valued function is just the derivative of each part. And here is very easy because t squared plus 1. So derivative of x squared, hopefully you remember, is 2x. So t squared would be 2t. And because we are adding a number, remember derivative of any number is 0. So that just disappears. So beware of the difference between multiplying by a number when the number is going to be kept as a constant multiple and adding or subtracting a number, then it's going to go away because it's just a number and slope of a number is 0, right? Number is a horizontal line with the slope of 0. All right, over here, derivative of 2t plus 1. Well, 2t is a line with the slope of 2. So that's just going to be 2, and then plus 1 doesn't matter. That goes to 0. Okay, and then it says, let's plug in 1. So if we plug in 1, we're going to find derivative vector at 1, and that'll be 2, 2, 2i, 2j. Now, let me explain how to draw these vectors on the chart here, on the graphic. Okay, first, the position vector. Well, we don't know what it is. We have to find it in order to start drawing it. And I don't know why they're not asking us, but we definitely want to do that. So let's go ahead and find derivative at 1. Derivative, I'm sorry, the position vector at 1 first. So what that means is just take the original expression and plug in 1 into it. Okay, so that's going to become 1 squared plus 1i plus 2 times 1 plus 1j. Okay, so that's just what's called the position vector. So I get 2i plus 3j. Now, when you draw the position vector, you always start at the origin. Okay, that's just the rule. So position vector always starts at the origin. And a vector that starts at the origin with components 2, 3 is very easy to draw. So you start over here, so we'll place a dot here. Then we're going to go 2 to the right and 3 up. 1, 2, 3. We always should wind up somewhere on the curve. So if it's not on the curve, then it's not a position because we want to know at time t equal 1, where is the particle? Well, the particle is at that point 2, 3, right? Okay, so I did that. But what about derivative? So now we figured it out. We found the derivative, we plugged in 1, and we got 2i plus 2j. One thing I want you to remember is that the derivative vector should never be drawn starting at the origin. We always draw it, we start it. The initial point of the derivative vector is always at the same place where the position was, the terminal point of the position. So you can see that the terminal point of the position was 2, 3. So the derivative vector should start at 2, 3. However, if you try to draw a vector, it'll just want to move the point, and you can't do that. So here's what I will do. I would just draw like a random vector, First, just draw something. And then reposition the start and end of that vector so that it matches to what you want. So I'm going to hover over the initial point here, and I'm going to drag it to this one, right? Because again, the velocity vector or the derivative, it's the same thing, should always be where the position was, where the particle was at that point in time. And particle was at 2, 3. Now, I want to draw vector 2i, 2j. So how do I do that? Well, I start over here, I go 2 to the right and 2 up. And there is my velocity or derivative vector. Now, one thing that you should know is that the derivative vector is always tangent to the curve, which is what happened here, right? You can see that this vector r prime, this right here, this is your r prime of 1, that is tangent to the curve. And also, it shows you the direction of motion. So as your parameter increases, the particle is going to go along that parabola, right? In the direction from bottom to the top. So the velocity vector, number 1, it's tangent. Number 2, it shows you the direction of motion. All right, so I drew that thing. Now let's go ahead and find the unit tangent vector. So here, whenever you see tangent, you should always pop in your head, okay, derivative. So here we have big T of t. So this is called unit tangent vector. And it's the same as the derivative because it's tangent, but it is normalized. So this is going to be r prime of t. How do we, what I call put a hat on the vector? What does it mean normalize? We want a unit vector. In other words, we want to divide it by its length so that the new vector has length of 1. So we're going to divide by r prime. Okay, magnitude. All right, so let's take the r prime, which was in general, it's not at 1, but it's in general. So r prime was 2ti plus 2j. Let's find its magnitude. So magnitude of this r prime thing. And everybody knows how to find the magnitude, right? We're going to take the square root, the first component squared. Now, very careful here, square the whole thing, plus the second component squared. So whenever I square the first component, this 2 will actually be distributed to both terms. So this is not just going to be, it's a very common mistake to say that, oh, that's just 2t squared. That's not right because this is going to be 2 squared t squared. Okay, so that's plus 4. So final answer here would be 4t squared plus 4. So what that means is my unit tangent vector, this big T guy, is going to be, I take each component here and I divide it by the magnitude to normalize it. So I'll take that square root, and that's going to be I plus 2, again, divided by that square root, 40 squared plus 4, j. Now, before we put it in, I just want to make one other, I guess, a note. Another common mistake that I see quite a bit. So when I see something like this, the itch is this, oh, well, you know, 40 squared, when I take the square root, isn't it just 2t? And then derivative, I'm sorry, square root of 4 is just 2. So wouldn't that be right? Oh, I simplified it. Look at how nice this is. Again, if you ever decide to simplify something, and you're like, oh, I probably can do that. Okay, you have a calculator, all right? Remember, you have a calculator. Let's put both of them. Let's define the f of, oh, it's not the f of x, it's f of t. And also define g of t the other side. And let's compare. Again, don't plug 0 or 1, because sometimes that actually will work. How about plug a 3 or whatever? Doesn't really matter. Is it the same? Nope, it's not. So are they equal? Absolutely not. You can never break square root at a plus sign. It does not work. Square root of a plus b is not square root of a plus square root of b. Or if this is squared, then that's just going to be a plus b or something. That does not work. Cannot break the square root at a plus sign. At the times, yes. So if this was multiplication, you could say that that's square root of a squared, which is a times b. So you could say, okay, that's a times b. But if it's plus, also assuming they're positive and everything, but if it's plus, nope, it doesn't work that way. So please do not try to do something that is not correct. And again, check it to see if it's right on the calculator. All right.